The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, let's start. Any questions? So we would like to have a perspective for this very common observation that if you have a gas that is initially in one half of a box and the other half is empty, and some kind of a partition is removed so that the gas can expand, then it will flow, and eventually we will reach to another equilibrium state where the gas occupies both chambers. So how do we describe this observation? We can certainly characterize it thermodynamically from the perspective of atoms and molecules. Well, we said that if I want to describe the configuration of the gas before it starts and also throughout the expansion, I will basically have to look at all sets of coordinates and momenta that make up this particle, and there would be some point in this 6n-dimensional phase space that would correspond to where this particle was originally. And then we can certainly follow the dynamics of this point. But is that useful? Because presumably I could start with billions of different types of boxes, or the same box at different instants of time, and I would have totally different initial conditions. And so the initial conditions presumably can be characterized through a density in this phase space. You can look at some volume and see how it changes, how many points you have there, and defines this phase space density rho of all of the Q's and P's, and how it evolves as a function of time. Well, one way of looking at how it evolves as a function of time is to look at this box and where this box will be in some other instant of time. And essentially then we are following a kind of evolution that goes along the streamline, and basically the derivative that we are going to look at involves changes both explicitly in the time variable and also implicitly through the changes of all of the coordinates and momenta according to the Hamiltonian that governs this system. So I have to do essentially a sum over all coordinates. I would have, let's say, the changing coordinate I, qi dot d rho by dqi, and then I would have pi dot, I guess these are all vectors, d rho by dpi. So essentially there are 6 n coordinates that implicitly depend on time, and in principle, if I'm following along the streamline, I have to look at all of these things. Now, the characteristic of evolution according to some Hamiltonian was that this volume in phase space does not change. And secondly, we could characterize, once we wrote qi dot as dh by dp, and pi dot as dh by dq. This combination of derivatives essentially could be captured and rewritten as d rho by dt is the Poisson bracket of h and rho. Okay. Now, one of the things, however, that we emphasized is that as far as evolution according to a Hamiltonian and this set of dynamics is concerned, the situation is completely reversible in time, so that some intermediate process, if I were to reverse all of the momenta, then the gas would basically come back to the initial position. And that's true. There's nothing to do about it, although that kind of seems to go against the intuition that we have from thermodynamics. So we said, well, in practical situations, I really don't care about all the 6n pieces of information that are embedded currently in this full phase space density. If I'm really trying to physically describe this gas expanding, typically the things that I'm interested in is at some intermediate time, whether the particles have reached this point or that point, and what is the streamline velocity that I'm seeing before the thing relaxes, presumably eventually to zero velocity. So there's a lot of things that I would need to characterize this relaxation process, but that is still much, much, much less than all of the information that is currently encoded in all of these 6n coordinates and momenta. So we said that for things that I'm really interested in, what I could, for example, look at is a density that involves only one particle. And what I can do is to then integrate over all of the positions and coordinates of particles that I'm not interested. Okay. Actually, I'm sort of repeating this to sort of introduce some notation. So as to not to repeat all of this integration variables, I will call dVi the phase space contribution of particle I. And actually, what I may be interested, this is something that if I integrate over P1 and Q1 is clearly normalized to unity because my rho, by definition, was normalized to unity. Typically, we may be interested in something else that I'll call F1, P1, Q1, P, which is simply n times this. So n times the integral product I to n d vi, the full rho. And why do we do that is because typically you are interested or used to calculating things in terms of a number density, like how many particles are within some small volume here, defining the density, so that when I integrate over the entire volume of F1, I would get the total number of particles, for example. So that's the kind of normalization that people have used for F. And more generally, we also introduced Fs, which depended on coordinates representing S sets of points, or S particles, if you like, that was normalized to be okay. Now, he said, okay, what I'm really interested in order to calculate properties of the gas as it expands in terms of things that I'm able to measure is F1. So let's write down the time evolution of F1. Well, actually, we said let's write down the time evolution of Fs along the way. So there's the time evolution of Fs. If I were to go along the stream, it would be dFs by dt, and then I would have contributions that would correspond to the changes in coordinates of these particles. Now, in order to progress along this direction, we said let's define the total Hamiltonian to have a simple form and certainly for the gas, it would be a good representation. I have the kinetic energies of all of the particles. I have the box that confines the particles, or some other one particle potential, if you like, that I will write in this fashion. And then we have the interactions between all pairs of particles. Let's write it as sum over I less than j, v of qi minus qj. Okay. Now, this depends on n set of particles, coordinates, and momenta. And then we said that for purposes of manipulations that we have to deal with, since there are s coordinates that are appearing here, whose time derivatives I have to look at, I'm going to simply rewrite this as the contribution that comes from those s particles, the contribution that comes from the remaining n minus s particles, and some kind of term that couples the two sets of particles together. And fine. This actually I didn't quite need here for until the next stage, because what I write here could presumably be sufficiently general. I could have here some n running from 1 to s. And let me be consistent with my s's. Then I have q n dot d fs by dqn plus pn dot dfs by dpn. Okay. So basically, if I just look at the coordinates that appear here and say, following this as they move in time, there is the explicit time dependence and all of the implicit time dependence. This would be the total derivative moving along the streamline. Now, qn dot, I know, is simply the momentum. It is dh by dpn. dh by dpn, I have from this formula over here, it is simply pn divided by m. It's the velocity, momentum divided by mass. This is the velocity of the particle. Pn dot, the rate of change of momentum, is the force that is acting on the particle. Now, what I need to do is to take the derivatives of various terms here. So I have minus du by dpn. And what is this? This is essentially the force that the particle feels from the external potential. So if you are in the box in this room, it is 0 until you hit the edge of the box. Okay, so I will call this Fn to represent the external potential that is acting on the system. What else? I have the force that will come from the interaction with all other guys. I will write here a sum over m dv of qm minus qn by dqn, du by dqn, sorry, dqn. Okay. What is this? This is basically the sum of the forces that is exerted by the mth particle on the nth particle. So I define it in this fashion. Okay. And basically, if this was the entire story, what I would have had here is a group of s particles that are dominated by their own dynamics. And if there is no other particle involved, they basically have to satisfy the Liouville equation that I have written, now appropriate to s particles. But of course, we know that that's not the entire story, because there are all these other terms involving the interactions with particles that I have not included. I mean, that's the whole essence of the story. let's say I want to think about one or two particles. There's the interaction between the two particles, and they would be evolving according to some trajectories. But there are all of these other particles in the gas in this room that will collide with them. And so those collisions are not something that we had in the Liouville equation, which was everything considered. So here I have to include the effect of all those other particles. And we saw that the way that it appears is that I have to imagine that there is another particle whose coordinates and momenta are captured through some volume for the s+1 particle. And this s+1 particle can interact with any of the particles that are in the set that I have on the other side. So there is an index that runs from 1 to s. And what I would have here is the force that will come from this s+1 particle acting on particle n, in the same way that this force was deriving the change of the momentum. This force will derive the change of the momentum of, I guess I put m here. But the thing that I have to put here is now a density that also keeps track of the probability to find the s+1 particle in the location in phase space that I'm integrating over. I have to integrate over all positions. So basically, there's, let's say, one particle that is moving along a straight line by itself, let's say. And then there are all of the other particles in the system. And I have to ask, what is the possibility that there is a second particle with some particular momentum and coordinate that I will be interacting with? Okay? So this is the general set of these BBGKY hierarchy of equations. And at this stage, we really have just rewritten what we had for the Liouville equation. So then we said, I'm really, really interested only in one particle things, rho 1 and F1. Let's focus on that. Let's write those equations in more detail. So for the first equation, I have that the explicit time dependence plus the time dependence of the position coordinate plus the time dependence of the momentum coordinate, which is driven by the external force, acting on this one particle density, which is dependent on P1, Q1 at time t. And on the right-hand side of the equation, I need to worry about a second particle with momenta P2 at position Q2 that will therefore be able to exert a force. Once I know the position, I can calculate the force that that particle exerts. What was my notation? Order was 2 and 1, dotted by d P1, and I need now F2. P1, Q2 at time t. Say, well, this is unfortunate. I have to worry about dependence on F2, but maybe I can get away with things by estimating order of magnitudes of the various terms. What is the left-hand side set of operations? The left-hand side set of operations describes essentially one particle moving by itself. And if that particle has to cross a distance of the order of L, and I tell you that the typical velocity of these particles is of the order of v, then that time scale is going to be of the order of L over v. So basically, the operations here will give me a v over L, which is what we call the inverse of tau u. And this is a reasonably long macroscopic time. OK, fine. Well, how big is the right-hand side? We said that the right-hand side has something to do with collisions. So basically, I have a particle in my system. Let's say that that particle has some characteristic dimension that we call d. OK? And this particle is moving with velocity v, or alternatively, you can think of this particle as being stationary, and all the other particles are coming at it with some velocity v. And if I say that the density of these particles is n, then the typical time for which, as I shoot these particles, they will hit this target is related to d squared nv, essentially the volume of particles. So over time t, this I have to consider a distance v tau x. V tau x n d squared should be of the order of 1. This gave us a formula for tau x. And essentially, the inverse of tau x that controls what's happening on this side is n d squared v. OK? So is the term on the right-hand side more important or the term on the left-hand side? Well, the term on the right-hand side has to do with the two-body term, right? So there's a particle that is moving, and then there's another particle, let's say, with slightly different velocity that is behind it. In the absence of collisions, these particles would just go along a straight line. Say they would bounce off the walls, but the magnitude of their energy and hence velocity would not change from these elastic collisions. But if the particles can catch up and interact, which is governed by v2, the v on the other side, then what happens is that the particles, when they interact, would collide and go different ways, and quickly their velocities and momenta and everything would get mixed up. And how rapidly that happens depends on this collision distance, which is much less than the size of the system. And therefore, the term that we have on the right-hand side in magnitude is much larger than what is happening on the left-hand side. There is no way, in order to describe the relaxation of the gas, that I can neglect collisions between gas particles. If I neglect collisions between gas particles, there is no reason why the kinetic energies of individual particles should change. They would stay the same forever. OK, so I have to keep this. So let's go and look at the second equation in the hierarchy. What do we have? We have d by dt, p1 over m d by dq1, p2 over m d by dq2, and then we have f1 d by dq1 plus f2 d by dq2 coming from the external potential. And then we have the force that involves the collision between particles 1 and 2. Essentially here, when I write down the Hamiltonian for two particles, there is going to be already for two particles an interaction term between them, and that's where the F12 comes from. F12 changes d by the momentum of particle 1, and then I should write F21 that changes momentum of particle 2, but F21 is simply minus F12, so I can put the two of them together in this fashion. This acting on F2 is then equal to something like integral over V3 F31 d by dP1 plus F32 d by dP2 acting on F3 P1 through Q3. Okay, are we going to do this forever? Well, we said let's take another look still at the magnitudes of the various terms. This term on the right-hand side still involves a collision that involves a third particle. And I have to find that third particle, so I need to have essentially a third particle within some characteristic volume. So I have something that is of that order. Whereas on the left-hand side now, I have a term that from all perspectives looks like the kinds of terms that I had before, except that it involves the collision between two particles. And essentially what it describes is the duration of that collision. So we said this is of the order of 1 over tau c, which replaces the L over there with some characteristic dimension. And suddenly this term is very big. And we should be able to use that. There was a question.
On the left-hand side of both of your equations, for F1 and for F2, should all of the derivatives that are multiplied by your forces be derivatives with respect to momentum, not with respect to coordinate, for dimensional reasons?
Well, let's go back here. I have a function that depends on P, Q, and T. Right? So then there's the explicit time derivative, d by dt, and then there is the q dot term, which will go with d by dq, and then there's the p dot term that will go with d by dp. And all of these have to be there. So I should have derivatives with respect to momenta and derivatives with respect to coordinate. Dimensions are, of course, important, so somehow what I write for this and for this should make up for that. As I have written it now, it's obvious, of course. This has dimensions of q over t. Q's cancel, I would have 1 over t. P over t, p's cancel, I have 1 over p. So here dimensionally is correct. So I have to just make sure I haven't made a mistake. Q dot is a velocity. Velocity is momentum divided by mass. So that should dimensionally work out. P dot is a force. What I have written here is force. So in a reasonable coordinate system. What did I do here? I made mistakes.
Force times d by dq is
d by dp.
and also in the first line.
Yeah.
Okay.
So why didn't you say that in a way that I didn't? So if I don't understand the question, please correct me before I spend another 5 minutes. Okay. So hopefully this is now free of these deficiencies. So this term is very big. Okay? And now compared to the right-hand side, in fact, we said that the right-hand side is smaller by a factor that measures how many particles are within an interaction volume. And for a typical gas, this would be a number that's of the order of 10 to the minus 4. And using 10 to the minus 4 being a small, we are going to set the right-hand side to 0. So now I don't have to write the equation for F3. Okay? Now, I'll answer a question here that may arise, which is ultimately we will do sufficient manipulations so that we end up with a particular equation known as the Boltzmann equation that we will show does not obey the time reversibility that we wrote over here. So clearly that is built in the various approximations I make. And so the first question is the approximation that I made here, did I destroy this time reversibility? And the answer is no. You can look at this set of equations and do the manipulations necessary to see what happens if p goes to minus p, and you will find that you will be able to reverse your trajectory without any problem. Yes?
Why, if, given that it's only the interaction term on the left side that's
very big.
Yes.
And is the reason why we can ignore the stuff on the right.
Right.
Why is it that we are then keeping all of the other terms that were even smaller before?
I will ignore them shortly.
Okay.
All right. There was the question of time reversibility, and again, you can sort of, this term here has to do something with three particles coming together and how that would modify what we have for just two-body collisions. Now, in principle, there is some probability to have three particles coming together and some combined interactions. You can imagine some fictitious model which, in addition to these two-body interactions, you cook up some three-body interaction so that it precisely cancels what would have happened when three particles come together. You can write a computer program in which you have two-body collisions, but if three bodies come close to enough to each other, they essentially become ghosts and pass through each other. That computer program would be fully reversible, and that's why sort of dropping this term is not causing any problem at this point. Okay. So what is it that we have included so far? What we have is a situation where the change in F1 is governed by a process in which I have a particle that I describe on the left-hand side with momentum P1, and it collides with some particle that I'm integrating over, but in some particular instance of integration has momentum P2. And presumably, they come close enough to each other so that afterwards, the momenta have changed over. So I have some P1 prime, and I have some P2 prime. And we want to make sure that we characterize this correctly. Now, there was a question about, well, this term is big. These kinds of terms are small. And so why should I basically bother to keep them? And it is reasonable. Basically, what we are following here is two particles in my picture that were ejected by the first box, and they collided to each other, or they were colliding in the first box. And as long as you are away from the boxes of the walls of the container, you really don't care about these terms. They don't really move very rapidly. Essentially, this is the process of collision of two particles, and it's also the same process that is described over here. So somehow I should be able to simplify the collision process that is going on here with the knowledge that the evolution of two particles is now completely deterministic, right? I mean, essentially, this equation by itself says take two particles as if they are the only thing in the universe, and they would follow some completely deterministic trajectory that, if you put lots of them together, is captured through this density. Okay, so let's see whether we can massage this equation to look like this equation. Well, the fourth term we have, except that here we have d by dp1, here we have d by dp1 minus d by dp2. Okay, so let's do this. Minus d by dp2 dot acting on F2. Did I do something wrong? The answer is no, because I added a complete derivative over something that I'm integrating over. So this is perfectly legitimate mathematically. All right, so this part now looks like this. I have to find what is the most important term that matches this. And again, let's think about this procedure. Essentially, what I have to make sure is that what is the extent of the collision and how important is the collision? If I have one particle moving here and another particle up there, they will pass each other. Nothing interesting will happen. So the important thing is how close they come together. It is kind of important that I keep track of the relative coordinate q which is Q2 minus Q1, as opposed to the center of mass coordinate, which is just Q1 plus Q2 over 2. Okay? So that kind of also indicates maybe it's a good thing for me to look at this entire process in the center of mass frame. So this is the lab frame. If I were to look at this same picture in the center of mass frame, what would I have? Well, in the center of mass frame, I would have the initial particle coming with P1 prime, P1 minus P center of mass. And the other particle that you are interacting with comes with P2 minus P center of mass. And I actually drew these to be vectors that are hopefully equal and opposite, because you know that in the center of mass, one of them, in fact, would be P1 minus P2 over 2. The other would be P2 minus P1 over 2. So they would indeed, in the center of mass, be equal and opposite momenta. And then along the direction of these objects, I can look at how close they come together. And so I can sort of look at some coordinate that I will call, let's say, absolute, well, let's call it A, which measures the separation between them at some instant of time. But then there's another pair of coordinates that I could put into a vector, which tells me how head-to-head they are. So if I think about their being now in the center of mass, two things that are approaching each other, they can either approach head-on, that would correspond to B equals to 0, or they could be slightly off the head-on collision. And there is a so-called impact parameter B, which is a measure of this additional fact. Okay? Now, why is that going to be relevant to us? Well, again, we said that there are parts of this expression that are of the order of this term. They're kind of not that important. And if I think about the collision and what the collision does, essentially I will have forces that are significant when I am within this range of interactions D. So I really have to look at what happens when the two things come close to each other. It is only when this relative parameter A has approached D that these particles will start to deviate from their straight line trajectory and presumably go to, say, in this case, P2 prime minus P center of mass. And this one presumably will go and eventually P1 prime minus P center of mass. But these deviations will occur over a distance that is of the order of this collision length D. And so the important changes that occur in various densities, in various potentials, etc., are all taking place when this relative coordinate is small. So things become big when the relative coordinate is small, and they are big as a function of the relative coordinate. So in order to get big things, what I need to do is to replace these d by dq's with the corresponding derivatives with respect to the center of mass. And one of them would come with a minus sign, the other would come with a plus sign. It doesn't matter which is which. Depends on the definition whether I make Q2 minus Q1 or Q1 minus Q2. So then we see that the big terms are essentially the force that changes the momentum and the variations that you have over this relative coordinate. So what I can do now is to replace this by equating the two big terms that I have over here. And the two big terms are d by dq of, okay, let's write it. So basically, I would have P2 minus P1 over M dotted by d by dq of F2. Okay? Now, there is some other approximation that I did. I mean, there's, as was told to me before, this is the biggest term, and there is the part of this that is big and compensates for that. But there are all these other bunches of terms, and there's also this d by dt. Essentially, what I have done over here is to look at a slightly coarser perspective on time. That is, in principle, the equations that I have over there tell me everything about particles approaching each other and going away, and I can follow through the mechanics precisely everything that is happening even in the vicinity of this collision. So if I have two squishy balls and I run my Hamiltonian properly, I can see how the things get squished and then released, and there's a lot of information. But again, a lot of information that I don't really care to know as far as the properties of this gas expansion process is concerned. So what we have done is essentially to forget about the detailed variations in time and space that are taking place here. And we're going to shortly make that even more explicit by noting the following, that this integration over here is an integration over phase space of a second particle. I had written before d cubed P2 d cubed Q2, but I can change coordinates and look at the relative coordinate Q over here. And then essentially what I'm asking is, I have one particle moving through the gas. What is the chance that a second particle comes with momentum P2 and the appropriate distance, relative distance Q, and I integrate over both the P and the relative distance Q. And this is the quantity that I have to integrate. Actually, let's do one more calculation, and then we will try to give a physical perspective. Now, in this picture of the center of mass, what did I do? I replaced the coordinate Q with a part that was the impact parameter, which had two components, and a part that was the relative distance. But what was this relative distance? The relative distance was measured along this line that was giving me the closest approach. What is the direction of this line? The direction of this line is P1 minus P2. This is P1 minus P2 over 2, but it doesn't matter. The direction is P1 minus P2. So what I'm doing here is I'm taking a derivative precisely along this line of constant approach. Okay? And I'm taking a derivative and I'm integrating along that. Right? So if I were to rewrite then the whole thing, then what do I have? I have d by dt plus P1 over M d by dq1 plus F1 d by dp1, don't make a mistake, acting on F1 P1 Q1 T. Okay, what do I have to write on the right-hand side? I have an integral over the momentum of this particle that I'm going to make a collision with. I have an integral over the impact parameter that tells me the distance of closest approach. I have to do the magnitude of P2 minus P1 over m, which is really the magnitude of the relative velocity of the two particles. I can write it as V2 minus V1 or P1 minus P2. These are, of course, vectors, and I look at the modulus. And then I have the integral of a derivative. So very simply, I will write the answer as F2 that is evaluated at some large distance plus infinity minus F2 evaluated at minus infinity. I haven't really, in principle, I have to integrate over F2 from minus infinity to plus infinity. But essentially, once I am beyond the range of where the interaction changes, then the two particles just move away forever. They will never see each other. So really what I should write here is F2 of, after the collision, I have P1 prime, P2 prime at some Q plus minus F2 P1, P2 at some position minus. So basically, what I need to do is to do the integration when I'm far away from the collision, all the way to when I am far after the collision. But really, I have to just integrate slightly below, after, and before the collision occurred. So in principle, if I just go a few d's in one direction or the other direction, this should be enough. OK, let's see now physically what this describes. And there is a connection between this and this thing that I had over here, in fact. So basically, this equation on the left-hand side, if it was 0, it would describe one particle that is just moving by itself until it hits the wall, at which point it basically reverses its trajectory and otherwise goes forward. But what you have on the right-hand side says that suddenly there could be another particle that I interact with, and then I change my direction. And so I need to know what is the probability, given that I'm moving with the velocity P1, that there is a second particle with P2 that comes close enough. OK? Now, there is this additional factor. What does this additional factor come from? It's the same factor that we have over here. That is, if we have a target of size d squared, and we have a set of bullets that their density is n, the number of collisions that I get depends both on density and how fast these things go. So the time between collision, if you like, is proportional to n, and it is also related to v. And so basically, that's what this is. I need some kind of a time between the collisions that I make. I have already specified that I'm only interested in the set of particles that have momentum P2 for this particular point in the integration, and that they have this kind of area or cross-section. So I replace essentially this d squared nv with the relative coordinate. This is the corresponding thing to d squared. And this is really a two-particle density. And essentially, this is a subtraction. The addition is because it is true that essentially I'm going with velocity P1, and practically any collisions that is significant will move me off kilter. So there has to be a subtraction for the channel that was described by P1 because of this collision. This term is the addition because it says that it could be that there is no particle going in the horizontal direction. I was actually coming along the vertical direction. And then because of a collision, I suddenly was shifted to move along this direction. So the addition comes from essentially having particles that would correspond to momenta that somehow, if in some sense reverse this and then put a minus sign, a reverse collision that would create something that was along the direction of P1. So I have to look at this. Okay. So here I also made several approximations. I said chief among them is that basically I ignored the details of the process that is taking place at scale of the order of d. So I have thrown away some amount of detail and information. And it is, again, legitimate to say, is this the stage at which you made an approximation so that the time reversibility was lost? And the answer is still no. If you are careful enough with making precise definition of what these Q's are before and after the collision, and follow what happens if you were to reverse everything, you will find that the equation is fully reversible. So even at this stage, I have not made any transition. I have made approximations, but I haven't made something to be time irreversible. That comes at the next stage, where we make the so-called assumption of molecular chaos. And basically, the assumption is that what's the chance that I have a particle here and a particle there? You would say it's the chance that I have one here and one there. In essence, saying that F2 of any P1, P2, Q1, Q2T is the same thing as the product of F1, P1, Q1T, F1, P2, Q2T. Okay? Now, of course, this assumption is generally valid. If I were to look at the probability that I have two particles as a function of, let's say, their relative separation, I certainly expect that if they are far away, the density should be the product of two one-particle densities. But you would say that if the two particles come to distances that are closest than their separation d, then the probability, then the range of the interaction d, and let's say the interaction is highly repulsive, like hardcore, then the probability should go to 0. So clearly, you can make this assumption, but up to some degree. Now, part of the reason we went through this process was to indeed make sure that we are integrating things at locations where the particles are far away from each other. So basically, I said that the range of that integration over A would essentially be someplace where they are far apart after the collision and far apart before the collision. So essentially, we have an assumption like that, which is in principle something that I can insert into that. But again, this having to make a distinction between the arguments that are appearing in this equation is kind of not so pleasant. So what we are going to do is to make another assumption, make sure that everything is evaluated at the same point. And what we will eventually now have is the equation that d by dt plus p1 over m d by dq1 plus f1 dot d by dp1 acting on f1 on the left-hand side is on the right-hand side equal to all collisions with a particle of momentum p2 approaching at all possible cross-sections, calculating the flux of incoming particle that corresponds to that channel, which is proportional to v2 minus v1, and then we here subtract the collision of the two particles, and we write that as F1 of P1 at this location Q1T, F1 of P2 at the same location Q1T, and then add F1 prime, P1 prime, Q1T, F2 prime, P2 prime, Q2T. Okay? So in order to make the equation eventually manageable, what we did is to evaluate all of the coordinates that we have on the right-hand side at the same location, which is the same Q1 that you specify on the left-hand side. So that immediately means that what you have done is you have changed the resolution with which you are looking at space. You have kind of washed out the difference between being here and here. So essentially, your resolution has to put this whole area that is of the order of d squared or d cubed in 3 dimensions into 1 pixel. So you have changed the resolution that you have. You are not looking at things at this fine scale. And so you are losing additional information here through this change of the resolution in space. And you have also lost some information in making the assumption that essentially the 2-point densities are completely written always as the product of one particle densities. Both of those things correspond to taking something that is very precise and deterministic and making it kind of vague and a little bit undefined. And it's not surprising then that if you have, in some sense, changed the precision of your computer, let's say, that is running the particles forward, at some point you've changed the resolution, then you can't really run backward. In fact, to sort of precisely be able to run the equations forward and backward, you would need to keep resolution at all levels. And here we have sort of removed some amount of resolution. So we have a very good guess that the equation that we have over here no longer respects the time reversal invariance that we had originally posed. And so our next task is to prove that indeed this equation goes in one particular direction in time and cannot be run backward, as opposed to all of the predecessors that I had written up to this point. Okay, any questions? Yes?
The last term in the equation, should F1 also be, F1 prime also be evaluated at Q1 dash?
Yes.
Q1 prime?
Q2 prime and Q1, not Q1 prime. There is no dash here.
Oh, also Q1.
Yes. Essentially, look at this equation. On the left-hand side, what are the arguments? The arguments are P1 and Q1. Okay? What is it that I have on the other side? I still have P1 and Q1. I have introduced P2 and B, which is simply an impact parameter. What I will do is I evaluate all of these things always at the same location, Q1. And then I have P1 and P2. So that's part of my story of the change in resolution, right? So when I write here Q1 and you say Q1 prime, well, what is Q1 prime? Is it Q1 plus B, Q1 minus B, something like this? I'm going to ignore that. And then it's also legitimate, and you should ask, what is P1 prime and P2 prime? What are they? Okay, so essentially what I have to do is I have to run on the computer or otherwise the equations for what happens if I have P1 and P2 come together at an impact parameter that is set by B. I then integrate the equations, and I find that deterministically that collision will lead to some P1 prime and P2 prime. So these P1 prime and P2 prime are some complicated functions of P1, P2, and B. So given that you know two particles are approaching each other at distance d with momenta P1 and P2, in principle, you can integrate Newton's equations and figure out what momenta they end up with. So this equation, in fact, hides a very, very complicated function here, which describes P1 prime and P2 prime as a function of P1 and P2. And if we really needed all of the details of that function, we would surely be in trouble. So fortunately, we don't. As we shall see shortly, we can kind of get a lot of mileage without knowing that. Yes?
So there was an assumption that all the interactions between different molecules are central potentials, right? So that the force of interaction between two particles lies along the line which connects them.
For the things that I have written, yes. So I should have maybe been more precise. I should have put absolute value here. But
so for if you have particles moving along one line towards each other, and B is some arbitrary vector, so you have two directions, they define a plane,
yes,
and after interaction, particles stay in the same plane. So can you reduce
particles stay in the same plane?
So if two particles were moving towards each other,
Yes.
and also you have in the integral your impact parameter,
Yes.
which points
Yes.
some other
Right.
direction. So
Okay.
these two directions,
Yes.
like how particles are flying and how B is aligned, they form a plane.
Exactly.
And
Yes.
after interaction, particles stand in
In
the
the same plane. Yes.
And my question is whether we can reduce the integral on the right from like two-dimensional integral in B
Yes.
into like employing central symmetry.
You could. Yes. Yes. So you could, in principle, write this as BDB, if you like. If that's what you want.
Yeah, roughly like
Yeah.
and 2 pi.
Yeah. So, yeah, you could do that if you have simple enough potential. Yes. Okay. Fine. So let's show that indeed this equation leads to irreversibility, and that we are going to do maybe here. So this, by the way, is called the Boltzmann equation. And there is an associated Boltzmann H-theorem, which states the following. If F satisfies, so if F of P1, Q1, and T satisfies the above Boltzmann equation, then there is a quantity H that always decreases in time, where H is the integral over P and Q of F1 log of F1. Okay? So the condition of irreversibility, as we saw in thermodynamics, was that there was a quantity entropy that was always increasing. So if we had calculated for this system entropy before for the half box and entropy afterwards for both boxes occupied, the second one would certainly be larger. So this H is a quantity like that, except that it's defined this way. It always decreases as a function of time, but it's certainly very much related to entropy. And you may have asked, why did Boltzmann come across such a function, which is f log f, except that actually right now you should know why you write this. Because when we were dealing with probabilities, we introduced the entropy of a probability distribution, which was related to something like sum over I pi log of pi with a minus sign. And that essentially up to this factor normalization n, this f1 really is a one particle probability. So up to this normalization n, you have a one particle probability, the probability that you have occupation of one particle phase space. And this occupation of one particle phase space is changing as a function of time. And what the statement is that if the one particle density evolves in time according to this equation, the corresponding minus entropy decreases as a function of time. Okay, so let's see if that's the case. So to prove that, let's do this. So we have the formula for H, so let's calculate the H by dt. So I have an integral over the phase space of particle 1. Particle that I've just called 1. It could be any, I could have labeled it anything. It's after integration, H is only a function of time. So I have to take the time derivative. The time derivative can act on f1, and then I will get the f1 by dt times log f1. Or I will have f1 times the derivative of log f1. The derivative of log f1 would be the f1 by dt, and then 1 over f1, and then I multiply by f1. And this term is simply 1. And
don't you want to be writing full derivative of f1 with respect to time rather than partial?
I thought we dealt with this before, that if we have essentially something that I am summing over lots of points, and these points could be position, and then I have S at location 1, S at location 2, S at location 3, and these are discretized versions of X. If I take the time derivative, I take the time derivative of this, which are partial derivatives. Okay? All right. Okay. So if I actually take the time derivative here, I get that the integral d cubed p1 d cubed q1, the time derivative, which would be the partial df1 by dt, is the time derivative of n, which is 0. The number of particles does not change. And indeed, realize that this is 1 integrated against df1 by dt. It's the same thing as here. So basically, this term will give me 0. All I need to worry about is integrating log f against df by dt. So I have an integral over p1 and q1 of log f against df by dt. But we have said that f, actually, let's write it, f1 satisfies the Boltzmann equation, right? So the f1 by dt, if I were to rearrange it, so if I rearrange it, I have the f1 by dt. I take this part to the other side of the equation. This part is also the Poisson bracket of a one particle H with F1. So if I take it to the other side, it will be the Poisson bracket of H with F1. And then there is this whole thing that involves the collision of two particles. So I define whatever is on the right-hand side to be some collision operator that acts on two powers of F1. So this is basically plus a collision operator F1, F1. And what I do is I replace this dF1 by dt with the Poisson bracket of H, or H1 if you like, with F1, and then the collision operator that I will shortly write explicitly, but for the time being, let me just write it as C of F1, F1. Okay. So there is a first term in the sum, let's call it number 1, which I claim to be 0. Typically, when you get these integrations with Poisson brackets, you would get 0, but let's explicitly show that. I have an integral over P1 and Q1 of log of F1, and then this Poisson bracket of H1 and F1, which is essentially these terms. I could alternatively write it as dH1 by dQ1 dF1 by dP1 minus dH1 by dP1 dF1 by dQ1. Okay, so I've explicitly written this form for the one particle in terms of the Hamiltonian. Okay. The advantage of that is that now I can start doing integrations by parts. So I'm taking derivatives with respect to P, but I have integrations with respect to P here. So I could take the F1 out, so I will have a minus. I have an integral P1 Q1. I took the F1 out, and then this d by dP1 acts on everything that came before it. It can act on the H1, so I would get d2 H1 with respect to dP1 dQ1, or it could act on the log of F1, in which case I will get essentially dH1 by dQ1, and then I would have d by dP acting on log of F, which would give me dF1 by dP1, and then the derivative of the log, which is 1 over F1. Okay? So this is only the first term. I also have this term, which I will do the same thing with. So
the term of log f, where the second derivative of Hamiltonian should be multiplied by log f.
Yes, thank you. Yes. Log F1. Good. Thank you. And then for the next term, I have F1. I have d2 H1, and now the other order of derivatives, dQ1 dP1. Now make sure I write down the log of F1, and then I have dH1 with respect to dQ1 dP1, and then I have a dot product with the derivative of log F, which is the derivative of F1 with respect to Q1 and 1 over F1. Okay. Now, the terms that are proportional to the second derivative, the order of the derivative does not matter. One of them is positive, one of them is negative, so they cancel out. And then I have these additional terms. For the additional terms, you note that the f1 and the 1 over f1 cancels. So essentially, these are just the product of two first derivatives. And I will apply the pi parts process one more time to get rid of the derivative that is acting on f1. And the answer becomes plus d cubed p1 d cubed q1. And then I have f1 d2h1 dp1 dq1 minus d2h1 dq1 dp1. And these two cancel each other out. And the answer is 0. OK, so that first term vanishes. Now, for the second term, number 2, what I have essentially is the first term vanished. So I have dh by dt is the integral over p1 and q1. I have log of f1. Now, f1 is a function of p1 and q1 and t. I will focus and make sure I write the argument of momentum for reasons that will become shortly apparent. And then I have to multiply with the collision term. The collision term involves integrations over a second particle, over an impact parameter, a relative velocity once I have defined what p2 and p1 are. I have a subtraction of my f evaluated at p1, f evaluated at p2, plus addition f evaluated at p1 prime, f evaluated at p2 prime. Okay. So again, eventually this whole thing is only a function of time. There are a whole bunch of arguments appearing here, but all of those arguments are being integrated over. Now, in particular, I have arguments that are indexed by p1 and p2, and these are dummy variables of integration. If I have a function of x and y that I'm integrating over x and y, I can call x z, I can call y t, and I would integrate over z and t, and I would have the same answer. So I would have exactly the same answer if I were to call all of the dummy integration variable that is indexed 1, 2, and any dummy variable that is indexed 2, if I rename it and call it 1, the integral would not change. And so if I do that, what do I have? I have the integral over q. Actually, let's get rid of the integration number on q. It really doesn't matter. I have the integrals over p1 and p2. I have to integrate over both sets of momenta. I have to integrate over the cross-section, which is relative between 1 and 2. I have v2 minus v1 rather than v1 minus v2 rather than v2 minus v1. But the absolute value doesn't matter if I were to replace these indices because it's an absolute value. Although v2 minus v1 goes to minus v1 minus v2, the absolute value does not change. And here, what do I have? I have minus f of p1 becomes f of p2, f of p1, plus f of p2 prime, f of p1 prime. But again, they are products. It doesn't really matter which order I write them. The only thing that really matters is that the argument was previously called f1 of p1 for the log, and now it will be called f1 of p2. just this name changed. Okay? And if I take this and the first way of writing things, which are really two ways of writing the same integral, and just average them, I will get 1/2 an integral d cubed q, d cubed p1, d cubed p2, d2b, v2 minus v1. I will have f1 of p2, p1, f1 of p2, plus f1 of p1 prime, f2 1 of p2 prime. And then in one term, I had log of f of 1 of p1. And I averaged it with the other way of writing things, which was log of f, let's put the two logs together, multiplied by f1 of p2. So the sum of the two logs I wrote as the log of the product. So I just rewrote that equation. If you like, I symmetrized it with respect to the index 1 and 2. And so the log f1 that previously had one argument through this symmetrization became 1/2 of the sum of the two. Now, the next thing one has to think about, what I want to do is to replace primed and unprimed coordinates. Okay? So what I would eventually write down is that I would have d cubed p1 prime, d cubed p2 prime, d2b, v2 prime minus v1 prime, minus f1 of p1 prime, f1 of p2 prime, plus f1 of p1, f1 of p2, and then log of f1 of p1 prime, f1 of p2 prime. So I symmetrized originally the indices 1 and 2 that were not quite symmetric, and I end up an expression that has variables p1, p2, and functions p1 prime and p2 prime, which are not quite symmetric, again, because I have f's evaluated for p's, but not for p primes. But what does this mean? This mathematical expression that I have written down here actually is not correct, because what this amounts to is to change variables of integration. This is in the expression that I have up here, p1 and p2 are variables of integration. p1 prime and p2 prime are some complicated functions of p1 and p2. Right? So p1 prime is some complicated function, I don't know, of p1, p2, and b, for which I need to solve in principle this Newton's equation. And similarly for p2 prime. So what I have done is I have changed from my original variables to these functions. So when I write things over here, now p1 prime and p2 prime are the integration variables. P1 and P2 are supposed to be regarded as functions of P1 prime and P2 prime. But you say, well, what does that mean? You can't simply take an integral dx, let's say f of some function of x, and replace this function, call it a new variables, and do integral dx prime. You have to multiply with the Jacobian of the transformation that takes you from the p variables to the new variables. Okay? And my claim is that this Jacobian of the integration is in fact unity. Okay? And the reason is as follows, that these equations that have to be integrated to give me the collisions are time reversible. So if I give you two momenta and I know what the outcomes are, I can write the equations backward, and I will have the opposite momenta go back to the minus the original momentum. So up to a factor of minus, you can see that this equation essentially has this character that P1, P2 go to P1 prime, P2 prime. Then minus P1 prime minus P2 prime will go to P1, P2. And so if you sort of follow that and say that you do the transformation twice, you have to get back up to a sign actually disappears to where you want. You essentially have to multiply by 2 Jacobians and you get the same unity. So you can convince yourself that this Jacobian has to be unity. So maybe next time, I guess we'll take it from there, explain this step a little bit more, and show that this implies what we had said about the Boltzmann equation.